A simple pendulum. Now, a pendulum consists of a bob, which is a small object attached to the end of a lightweight string. A pendulum moves similar to simple harmonic motion in the sense that it moves back and forth, it oscillates through an equilibrium point, which is when it stands still or vertically, and it moves the same displacement back and forth through the equilibrium point. To calculate the displacement of a pendulum, you have this equation, which is x equals L times theta. L being the length of the cord, and theta being the angle that it makes with the arc as it moves through the equilibrium point, like this. Now, is a pendulum moving in simple harmonic motion? We have an equation here, which is for the restoring force of a pendulum, which is F equals negative mg, mass times the acceleration of gravity times the sine of the angle. That's the key, the sine of the angle. The force is proportional to the sine and not the angle itself, which makes the motion of a pendulum not simple harmonic motion. Now, that is for normal, general angles. For angles less than 15 degrees, the sine of an angle, when converted to radians, is almost the same as a normal angle. So it can be neglected. So we have that F equals negative mg. Now, negative mg theta. Now we know that theta equals x over L from the equation I gave here. So you can say that for small angles less than 15 degrees, force equals negative mass times acceleration of gravity over L times x. And that is simple harmonic motion because Hooke's law applies to it. Here is a drawing I made to show that how angles less than 15 degrees make the pendulum move in simple harmonic motion. If you have a book, you can look it up. It is drawing figure 1, figure 11, and 12. Now, the period of a pendulum is calculated by this equation, 2 pi square root of L over G. And the frequency is just 1 over period, so it's 1 over 2 pi times square root of L over G. Now, in this example, they ask us to find the acceleration of gravity, or G. Now, they give us the frequency, which is 0.8190 hertz, and the length of the cord, which is 37.10 centimeters. Now, we have an equation that uses frequency, which is F equals 1 over 2 pi times the square root of G over L. Now, to get G, you just solve this equation for G, and you get the G equals 2 pi times frequency squared times L. When you plug in the values and correct the units, you get it's 6.283 times 0.8190, that is the frequency, squared times 0.3710 meters, which is the length converted to meters because those are the SI units. When you calculate these, you get that the acceleration due to gravity is 9.824 meters per second squared. Damped harmonic motion. The amplitude of any oscillating spring or swinging pendulum will slowly decrease in time until its oscillation stops altogether. This happens because of an effect called damping. The amplitude slowly decreases every time the system oscillates till it comes to rest eventually. Air resistance and friction are usually the causes of damping. Now, here's a graph showing the effect of damping and amplitude over time and how it comes to rest. Simple harmonic motion does not exist. It is not real. Not a single system does not have damping. Now, why do we use simple harmonic motion? Because it makes it easier for us to calculate any type of equation that has to do with this type of problems. Now, if the damping of any system is small enough, we can neglect it and use simple harmonic motion. But if the damping is not small, we have to take it into account. And that's why damping is divided into three types, which is underdamped, overdamped, and critical damping. Here is a graph showing the three types of damping in graphs of amplitude. The first one, underdamped, is the weakest damping. This is the one that takes the longest time to come to rest. We can see it here, how it takes the longest time. And then overdamped, which is B, is the one which is the second slowest. It has a lot of damping, but the system still takes a little bit of time to come to rest. And then it's critical damping. When the damping is so intense, the system maybe oscillates once or twice before coming to rest. It is the quickest of the three for a system to come to rest. Every single system has damping. Either small or big, there is damping, and it is not possible for a system to be in simple harmonic motion. We just use simple harmonic motion to make it easier for us to calculate any type of stringing problem or pendulum problem that exists. Force, vibrations, and resonance. When a vibrating object is set in motion, it has its natural frequency. The frequency it always has when it vibrates naturally. Now, some objects have external forces acting on them that changes their vibrations, and those are called forced vibrations, which have their own frequency, different from the natural frequency of such objects. Now, natural vibration or natural frequency will be now denoted by F0 or F initial. The equation for F initial is 1 over 2 pi times the square root of k over m, the constant over the mass. And the forced vibration will be denoted by F. The amplitude of a wave of a vibration is normally denoted by calculated by the difference of F and F0. But when F equals F0 or is very close to being equal to F0, resonance happens. Now, when resonance happens, the amplitude of a wave is largely amplified, as we see here. The amplitude for a wave with light damp is really high, and as I explained in the previous section, heavy damp makes the amplitude of a wave lower, so the resonance for the amplitude for B with heavy damp is lower, but it's still amplified with resonance. And now, resonant frequency is just another name for natural frequency, which is F0. Think of it like this. If you swing a child, if a child is in swings and you push him at random times, he will just bounce all over the place. But if you push him with the natural frequency of the swing, he will go much higher and much faster. If you go with the motion of the swing, you will get a higher altitude in the swing. But if you go against the vibrations or the frequency of the swing, you will just get random pushes everywhere and the kid might fall off the swing. That is resonance, natural and forced vibrations. Wave motion. Waves travel in many ways, and there are different kinds of waves, but we're going to focus in this section on mechanical waves. Mechanical waves are the type of waves that need a medium to travel, be it air, water, metal, whatever you want, but it needs something to travel through. For example, sound waves, they travel through air. That's why in space there's no sound, because there's no air, so sound waves cannot travel, that don't have a medium to travel, so they cannot go anywhere. Now, If you've ever thrown a rock at a puddle or even spoken, you've created a mechanical wave. The source of any mechanical wave is a vibration. Be it a pulse or a periodic wave, the source of any mechanical wave is a vibration. What's the difference between a pulse and a periodic wave? A pulse is a wave created by a single vibration. Let's say you grab a rope and just hit it down once, you create a pulse, a single wave. Or a periodic wave is when you continue vibrating or oscillating something to keep it vibrating. For example, you grab a rope and you keep grabbing it and you keep pulling it up and down, you're creating vibrations, you're creating waves. Now, a misconception is that waves carry matter. They don't, they carry energy. Think of a pond and leaves on the top of the water. When you splash the water, the waves move the leaf up and down, but the leaf doesn't actually go on with the wave, it stays in a spot. That's why a particle in the pattern of a wave does not travel with the wave, travels upon a certain point in equilibrium, like here. This is a particle, and there are two different velocities. When the hand is oscillating the rope back and forth, the particle moves up and down with the wave, but the wave moves from left to right. It's different. Waves transfer energy, not matter. Now, there are different parts of waves. There's the crest, which is the highest part of the amplitude or wave, the trough, which is the lowest part, the amplitude, which is the distance from the equilibrium point, and the wavelength, which is the length between any two equal parts of a wave. Now, there is something called the wave velocity, which is calculated by 1. The wavelength times the frequency. It's easy. How many times a certain part of the wave pass a point in a second? But remember that mechanical waves need a medium to travel. So you also need to take into account the medium the waves travel in. Now there's an equation to calculate the wave velocity for waves that travel in a string or a cord, which is this one. Wave velocity is equal to the square root of the force of tension of the rope over the mass of the rope over the length. Ft over m over L. You square root the answer and you get the wave velocity for a wave traveling through a cord or a string. Now, this example asks us for the wave velocity of a wave with a wavelength of 0.30 meters through a wire that has a mass of 15 kilograms, the wire has a length of 300 meters, and a force of tension of 1000 newtons. Now, I gave you the equation to get the wave velocity when a wave travels through a wire, which is the square root of the force of tension over the mass over length. We plug in the values that are given to us and we get that its velocity is the square root of 1000 over 15 over 300, which equals to 140 meters per second. Then they ask for the frequency of the wave. If you rearrange the first equation of wave velocity, which is wave velocity equals wavelength times frequency, you get that the frequency equals velocity over wavelength. You got velocity in the first part of the exercise, so it's 140 meters per second over 0.30, which equals 470,000 hertz. 470 hertz, excuse me. Transversal and longitudinal waves. This section is very simple. It just talks about the two types of waves there are. There's a transverse wave that is a normal wave we know that goes up and down. This type of wave, that is the wave in water, the ropes, and it goes up and up. And there's the longitudinal wave. That's the wave that composes the sound waves or springs. it consists not of going up and down, but of compressions. The waves compress and then decompresses and then compresses again. The distance between compressions is the wavelength. And same as the transverse waves, the frequency is how many compressions go through a point in a second. Now, here are some examples of longitudinal and transverse waves. Transverse have rope, the water waves. Longitudinal have sound waves, springs. But there is a catch in calculating the velocity of a longitudinal wave. Well, it is a mechanical wave, so it needs a medium. But depending on the medium, there's a different way. Let's say for a chord, the velocity is calculated by the square root of the elastic factor of the chord over the inertia factor. Then, for a solid rod, a straight solid rod, the velocity is calculated by the elastic factor over the density. And then, for a liquid or a gas, it is calculated by the buoyance over the density. Here you can see a drawing of the two waves. The longitudinal with the compressions, and the normal transverse wave that goes up and down. In this example, they ask us to find the wavelength of a wave with a density in water with a density of 1.025 times 10 to the third. Remember that salt water is a little bit more dense than normal water, and the bulk moduli of 2.0 times 10 to the 9. Now, since it's a fluid, it's salt water, we need to use this equation, is V equals square root of the bulk moduli over the density. We first need to find the velocity. So we plug in 1.025 times 10 to the third over 2.0 times 10 to the 9, square root that, and we get 1.4 times 10 to the third meters per second. That's the velocity. Now we use that to find the wavelength. Wavelength is equal to the velocity over the frequency. So you use the value of the velocity you got and you put 1.4 times 10 to the third over 2.0 times 10 to the fifth hertz equals to 7 millimeters. There you have your wavelength. Now for the second part of the problem, you just multiply the distance the wave traveled times 2, since it's on its way to the location and back to the whale, and divide it by the distance, because it's a normal time equation, and it's 2 times 100 meters, so 200 meters divided by 1.4 times 10 to the third equal to 0.14 seconds. In this example, they ask us to find the intensity of an earthquake at a second point far from its source. First, they give us radius 1, which is 100 kilometers, and that intensity at that point, which is 1.0 times 10 to the 6th watts per meter squared. Then they tell us to find the intensity of the earthquake at 400 kilometers of its source. As I said, I2 over I1 equals R1 squared over R2 squared. The further you are, the bigger the radius, but the smaller the intensity. The closer you are, the bigger the intensity, but the smaller the radius. We apply the equation directly and plug in the values. We solve for I2 to get the second intensity, and we get that the second intensity is equal to R1 squared over R2 squared times I1, which we have already. We plug in the values. 100 squared over 400 squared times 1.0 times 10 to the 6th gives us the second intensity at 400 kilometers is 6.3 times 10 to the 4th watts per meter squared. Again, just remember these, memorize these equations, and you'll be fine. Energy transported by waves. Pay attention because this might get a little tricky. First, as I said before, waves transfer energy, not matter. So the first thing we need to know is that energy is transferred through vibrations between the particles of the medium of the wave. What that means is that the particles vibrate and transfer the energy to each other as the wave goes through the medium. Now, for a sinusoidal wave, the particles move in simple harmonic motion, and that gives us that each particle has energy in 1/2 k a squared. That's not important right now, just keep that in mind. Now, the energy transported by a wave is proportional to the square of its amplitude. That is important. Proportional to the square of its amplitude. We're going to learn a new term here. It's called intensity. Intensity is power over area. And don't forget that power is energy over time. Since it's proportional to energy, intensity is also proportional to the square amplitude of a wave. So, and the unit of power is watts per meter squared. So now that we know that intensity is also related to the amplitude squared, we can talk about different types of waves. An example of a new kind of wave is a spherical wave. What do I mean by a spherical wave? It's a wave that goes in all directions. For example, sound. When you say something in the air, the sound waves go to all directions. Another example is light. Another example is, I don't know, there are lots of examples. So, if you want to calculate intensity of a spherical wave, it is power over area, and the area of a sphere is 4 pi r squared. So, in spherical waves, the intensity is calculated by power over 4 pi r squared. Now, you know that a wave can be a pulse or a periodic wave. So when it's a periodic wave, the source is constant; it keeps going. So if the power output of the wave is constant, as the wave gets away from its source, the intensity lowers. So the intensity is proportional to the inverse of the radius squared of the source of the wave. Here it is. The inverse radius squared of the source of the wave, the intensity. The same thing applies for 2 points away from the source. We can see that intensity 2 over intensity 1 is equal to the radius 2 squared over radius squared 1. So if you calculate 2 points away from the source, the further you are from the source, the lower your intensity is going to be, but the higher your radius is going to be. Now, your amplitude is proportional to the inverse of the radius of the source of the wave, because the closer you are to the source, the higher is your amplitude. So the same thing applies for the amplitude. Amplitude 2 over amplitude 1 is equal to radius 1 over radius 2. The further away you are from the source, the bigger is going to be your radius, but the closer you are, the bigger is going to be your amplitude. So A2 over A1 is equal to R1 over A2. Just to clarify, to remember, power is energy over time, and intensity is power over area. So that's why it's related to the amplitude, because energy transferred through vibrations between particles of the medium, and the energy transported by a wave is proportional to the amplitude squared. Reflection and transmission of waves. When a wave strikes an obstacle, like a wall or a pole, some of it or all of it is reflected. First, for example, imagine you tie a rope to a pole, like you have a rope on a tabletop, and you fix one end. And then you have another rope, and at the end is free. When you make a wave in the rope, in the fixed end, this is the reflection that will happen. The wave will travel through the rope, will hit the pole or the fixed end, and will come back down, backwards to the rope. Since it's reflected against the fixed end, the wave is driven downwards and reflects downwards through the rope. Now when the end is free, when you make the wave through the rope, it comes back from the top. Energy comes back from where it went instead of from the bottom. Now, there's another type of wave, like the 2 or 3-dimensional wave, like the spherical wave we talked about in the past section. These have different types of reflections. First of all, their waves have different parts. For example, a sea wave. It has a wave front, which are what compose the wave, what are typically the wave we see at the beach. And then there's rays that go in the direction of where the wave is traveling. Wave fronts and the rays. A 2 or 3-dimensional wave that has gone too far from its source, let's say a wave that crashes into the beach, is called a plane wave because it loses its dimensions. It becomes a one-dimension wave. Since it's too far from the source, it's become too small, and it's just a plane wave, one dimension. And then there is the law, law of reflection for rays. Let's say, for example, you reflect a ray of light to a mirror. The law of reflection says that the angle of reflection is equal to the angle of incidence. What does this mean? Is that the angle at which you point the ray at the mirror is equal to the angle that the ray is reflected from the mirror. So these are the types of reflections and transmissions of waves that there are. Transversal waves, fixed end, free end, the 2 or 3-dimensional wave with the wave fronts and the rays, and then there's the law of reflection for rays reflected from a flat surface.